All right. So hi, everybody. Thanks again for tuning in today. This week, our seminar speaker is Dr. Aster Cowart, who is currently a postdoctoral researcher working with the Planetary Science Institute. Dr. Cowart is a planetary scientist whose research focuses on studying the surface geology of Mars at varying scales, and they also do that by combining different data sets, in particular data sets acquired at different wavelengths, including visible images and thermal infrared wavelengths acquired from satellites and also rovers. Again, so spanning again, just different scales, different wavelengths. Dr. Cowart earned a bachelor's degree in geology from Southern Illinois University Carbondale, and then a PhD in geosciences from the Stony Brook University in New York, where I actually met them a long time ago, and they were a grad student, and where they actually just finished up this past year. And then again, since then, they've been in their current position with the PSI. And so thanks again for taking the time to talk with us. Take it away. Thanks again.
All right, thank you, Francis. So today's talk, I'm just gonna try to cover some of the work that I did during my dissertation and transitioning into my postdoc. And this really takes us from the orbital scale down to the Hanlon scale. Let's see, there we go. So I guess the motivating question is, why are we even interested in Mars? And really the overarching factor is that it's among the oldest and most easily accessible example of Earth-like surface processes in our solar system. Venus might have different processes going on that are also Earth-like, but the atmosphere really prevents us from getting a good look at it in any way whatsoever. So here's just some of the different landforms that we see preserved on Mars. We have these really beautiful delta complexes. This is the Eberswald crater complex. We have these well-preserved lava flows. This lava flow here is probably about 1 billion years old. We see sedimentary sequences everywhere, and we have active glaciers. Just a really cool world to study. But what's really interesting about it is that the geologic record seems to be a planet that operates in fits and starts. There's just a lot of periodic activity, and over time, it seems like those pulses of activity got fewer and further between. So really kind of the question that we ask ourselves when we look at Mars is, how did this superficially Earth-like world that we can see all of these wonderful Earth-like landforms become the arid, kind of barren world that it is today? So just to back up and kind of describe some of my terms for people who may not work on Mars, I'm going to be referring a lot to the Martian geologic timescale. This is basically how we divide up segments of time on Mars. And this timescale kind of dates back to the Viking days, looking at crater density. There's a large part of the surface where we see very dense cratering, large craters that overlap one another. Basically craters so dense that forming a new crater destroys an old crater. As we move through times, there are also large plains where there are quite a few craters, but nowhere near as large, nowhere near as dense. And as we move forward closer to the present, we see very few craters, and these suggest to us that it's a relatively young surface. So these really densely cratered surfaces are defined as the Noachian, and this our estimates for this age range between 4.1 and 3.7 billion years ago. The moderately cratered surfaces are the Hesperian. This is about 3.7 to 3 billion years ago. And everything since then is the Amazonian. And the Amazonian is kind of defined by these really large volcanic provinces. Here in this image, you can see Olympus Mons here, and then some of these large Tharsis volcanoes here. Just kind of showing you the distribution of surfaces of those ages, you can see that a large part of the southern hemisphere is kind of Noachian material. Large parts of the northern hemisphere are Hesperian and Amazonian material. And these are the volcanic centers here, and here. And you can see that the Amazonian is largely confined, or Amazonian surfaces are largely confined to these areas. These are probably the areas where we're having the last gasps of geologic activity today. So if we want to understand if we want to really understand a terrestrial planet, we really need to go where the rocks are. So a few questions. Where do we find the rocks? What should we do when we find them? And when we get there, what are we actually seeing? So I'll walk through my toolkit real quick. First is the thermal emission spectrometer. This is a thermal infrared spectrometer. It basically measures the amount of light emitted as heat across a pretty wide spectrum. The resolution of this instrument's relatively coarse, it's about 5 kilometers, but it can let us measure the surface temperature and the spectrum of the surface, and which will help us figure out what types of minerals are present. There's the baby version of this, PSAS, not as many channels, but a much higher spatial resolution. We can get up to 100 meters per pixel with this, and it can do the same thing. Unfortunately, because there aren't as many spectral channels that we're measuring, we can really only look at relative differences in composition as opposed to specific mineralogy like we can with TESS. And to back up and explain what thermal infrared spectroscopy is, basically photons in this wavelength regime will resonate with molecular bonds between minerals, and this will produce a spectral fingerprint. And so we measure this fingerprint by comparing the light emitted from a surface and then a theoretical perfectly radiating material, which we call a black body, at the same temperature. We calculate that temperature by looking for, essentially estimate the surface temperature by finding points where we know that the spectrum is going to be closest to this theoretical perfectly emitting body, and then work from there. So emissivity is basically the ratio of the measured spectrum to a black body spectrum. PSAS specifically, we collect data between about 7 and 15 microns, and this wavelength region corresponds primarily to silica bonding. Silicate rocks are kind of defined by the degree of silica polymerization, basically how well networked are these silica minerals. And as these silica atoms or these silica molecules get more interlinked with one another, the bond length changes in a way that measurably affects the emission spectrum. So highly polymerized silicate minerals like quartz and feldspar have emissivity minima at shorter wavelengths. And poorly polymerized silicate minerals have emissivity at longer wavelengths. And I'll come back to this in a little bit. Looking at PSAS, we also use decorrelation stretch imagery. This basically just enhances the spectral differences within an image. This is using bands, this image here is using bands 8, 7, and 5. And this is really kind of looking at the shape of the spectrum and the silicate absorption region. So in images like this, keep in mind that these are all relative differences. There's no absolute difference that you can tell from these types of images. But magenta and purple rocks have emissivity minima towards longer wavelengths, so they correspond to more silica poor rocks. These yellow and green colors correspond to rocks with or to more silica rich rocks. Their emissivity minima is at shorter wavelengths. I also use visible light cameras, and these really help us look at geomorphology. The context cameras is a very important instrument that I use. It looks at basically 30-kilometer wide strips of land at a given time, and these strips can be hundreds of kilometers long. And these let us do things like measure crater density, kind of give us an overview and context of landforms. And I also use the high resolution imaging experiment, or HiRISE. This is a really big telescope. If I remember correctly, it's a 16-inch telescope that's bolted onto the side of the Mars Reconnaissance Orbiter. and we can get images that basically resolve objects the size of a dinner table on the surface, which is really fantastic. It lets us measure things like layer thickness, layer continuity, and then really just gives us a good view of these landforms. So where can we find rocks on Mars? It's actually really hard to find rocks from orbit because the Martian surface is just coated with all sorts of unconsolidated materials, which we'll just kind of lump into a collective term called regolith. These can be sand, fractured rocks, airfall dust, all sorts of different stuff that is just moving around and getting mixed together. And this mixing makes this regolith relatively homogeneous. Whatever rocks these came from, they've gotten so mixed up that if we looked at the spectrum of these, we're basically looking at the spectrum of a surface for dozens to hundreds of kilometers in area. And another problem with this regolith is that it can also mask a lot of the underlying rock structures. Getting from the top of the regolith down to actually intact rock material can be dozens of meters. So just to show an example of these regolith coated surfaces, this is a Hesperian volcanic plain. So the surface is about roughly 3.6 billion years old. And you can see there's a lot of craters, but really the terrain is very soft looking. It's just got this stuff that diffuses across the surface. Large exposures of rock are actually pretty rare. And like even when we look at geologically young for Mars lava flows, say something less than a billion years old, we see extensive regolith covers and thick dust coatings. Part of this is probably cyclical. You have dust that is deposited on top of rocks now, and the climate changes, and where rocks are exposed changes over time. But even though these are thin covers, they really prevent us from looking at the spectra of the rock. And if we compare these surfaces to the moon, we would expect to see regolith covers up to 100 meters in thickness on some of these really old surfaces. But what is interesting is, and I'll touch on this in a moment, is that Mars's oldest surfaces really appear to have the most extensive rock exposures associated with them, which is kind of a weird paradox. So to get around these issues of regolith, we use thermal inertia to look for exposures of intact rock. Basically, thermal inertia is how quickly, or really how much energy does it take to change the temperature of a rock or a material, and how long it takes to change the temperature of a material, and this influences the rate at which it changes temperature. So if you imagine the sun coming up and over the course of the day, the surface is getting warmer, surfaces with low thermal inertia will heat up very quickly and then they'll cool down very quickly. And these correspond to materials like dust or sand. You've probably been to the beach, you've felt how hot the sand gets in the midday. You would probably prefer to be walking on the sidewalk. And so these high thermal inertia materials change temperature very slowly. And these are usually exposures of rock or loose sediment that has just been kind of cemented together, or not cemented together, but kind of interlocking grains that where it's consolidated. So there have been a few previous global studies that look at thermal inertia and try to figure out where the rock is. I think the biggest one is probably Chris Edwards and his students, who were looking at THEMIS imaging of the surfaces and just using a threshold value of thermal inertia, and if a themis or if the location had higher than that, it was probably rock. And so we see that these exposures are primarily found as small exposures in canyon walls and crater rims. That sort of makes sense. These are where the wind is most easily able to clear off the dust. These are steep slopes, so regolith's not accumulating on them. So that makes sense. But a handful of these exposures are found in these really ancient craters and within the cratered highlands, these really old surfaces that I was talking about. My advisor, Deanne Rogers, she identified some exposures of rock in the Terra Sabea highlands that weren't picked up by this previous thermal inertia survey. And she noted a correspondence between the exposed rock and elevated olivine signatures. So I didn't talk about this instrument, but this is visible near infrared. It sees olivine, or it can pick out olivine spectra, and where we basically see the strongest signals basically sitting right on top of these dark bedrock areas in the themis imaging. So with a bunch of work, she and her students came to the conclusion that these were probably Noachian aged flood basalts. But there are a lot of issues in interpreting some of these bedrock plains because we don't really see a lot of them. We don't know if that map was complete. And so really we don't understand whether these are representatives. And also we just see this difference in regolith cover. Why are these Noachian flood basalts, which should have more regolith on top of them, more accessible to study than Hesperian volcanic plains, which are lava flows with more regolith on top of them? So just comparing these again, yeah, these Hesperian volcanic plains on the left, lots of regolith. These presumably flood basaltic bedrock plains in Terra Sabea with very little regolith cover. So that's where I come in. I'm looking at my first project as a grad student was to map out and characterize these bedrock plains. And really what I'm doing, or what I was doing, was figure out whether or not this inventory was complete. After I identified bedrock plains, I would go in and look at the landforms that are present. I would look at the spectral properties, check out whether or not olivine signals are really closely associated with these bedrock plains, or if it's just a weird select few that have it. And if possible, if these are maybe clastic plains, can we identify source sink relationships? And really, at the end of the day, what I wanted to do was tie bedrock plain formation to specific processes. So the first step was to use a test temperature map, these really coarse 5-kilometer resolution pixels, to identify these large bedrock exposures. The reason I use this is basically because these pixels are really big, and if there's a high thermal inertia that we see within these pixels, there's probably a lot of rock there. Basically, everything inside the pixel averages out. So if there's a lot of sand, you're going to have a low thermal inertia, even if there is a significant amount of rock. So having observed these, or having identified these regions of high test thermal inertia, I'd go in with CTX imaging and just verify that yes, it looks like rocky material is present on the ground. And if there are, and this is kind of to filter out some of the artifacts associated with test thermal inertia, because atmospheric conditions, dustiness, those can cause thermal inertia to appear artificially high at some times of year because it's being overcorrected. So after I verified that these are valid test thermal inertia signatures, I would go in with themis temperature maps and and just map out these exposures of rock. So just this figure kind of shows that. Here's a test signal. Here's what the surface looks like in Themis. You can see that these surfaces, sorry, this is nighttime temperature, so rocks are warmer and should be brighter. So you can see that the rocks here are, you can see that the surface here is warm, surrounding material is cold. This is probably bedrock. And there are some situations where we saw signals in tests, but not really a clear exposure. Yeah, there's these little bits of bright terrain that are probably rock, but nothing really overall consistent. So if I saw these and I could be reasonably confident that there was some sort of rock there, I just kind of put a squiggle line around it and someone else can deal with it. So over the course of the survey, I picked out 139 bedrock plains, and 13 of these regions with kind of that might have extensive rock exposure, but I can't really tell what's going on with them. I'm really going to focus in on 2 for the purposes of this talk in the Terra Sabea Highlands here, and the Terra Cimmeria Highlands over here. And you can see that already that the sizes of these bedrock plains are very different, and that suggests perhaps some different process is responsible for forming them. So having identified these places, I go in with CTX again and really start characterizing the surface texture. One of the things I wanted to look at was the amount of crater retention. Basically, we expect small craters to form at a certain rate, and the crater sizes are proportional to one another. You expect a certain number of small craters for every crater of a certain size, you expect a certain number of craters of a smaller size or larger size. Small craters are really easily removed by erosion. So if there is any erosion, you should see a predominant, or you should see the crater statistics start skewing towards larger craters than more larger craters than you would expect. Sort of relatedly, I was also looking at surface degradation. These are also influenced by erosion, but this is more kind of a qualitative measure of how textured the surface is. Are we looking at planar surfaces that are largely defined by craters, like we see over here, or are we looking at these really deeply eroded, these really deeply textured surfaces, or something in between? While I was doing this, I was also trying to identify landforms that might help us figure out how these bedrock plains formed. Layering, low-like textures, sinuous ridges, conical mounds. And I'll point out a really spectacular example here of a sinuous ridge. These are usually associated with topographically inverted channel deposits. Basically, you had material there, you eroded into it, deposited something inside of it, and then whatever was deposited inside of it ended up a little bit harder than that surrounding rock, and then it erodes away, and you're left with this, you're kind of left with the channel fill material only. And these can be really big. This is a pretty spectacular example here on Mars. But we see a lot of these on Earth. Here's May for scale out in Utah at one of these inverted channels. Okay, so after I look at surface degradation, I also go in and look at the spectra. We developed a spectral difference parameter. This basically just summarizes the overall spectral difference between bedrock exposure or between the bedrock and the surrounding material. So basically, we looked at how different we scaled the spectra to the same depth, and then measured the difference in emissivity at each channel, and then summed that. And so you see that very similar spectra have small scores, very different spectra have large scores. To look at the olivine problem, we just used a simple mixing model. If we look at the surrounding material and add olivine to it, does that give us what we see in the bedrock? And this allows us to estimate the amount of olivine that was present in the surface. So just to kind of summarize everything that I did, in Terra Sabea, we see these very large spectral differences down here. Overall, they seem to be pretty high and pretty substantial. And in Terra Samaria, we saw minor to moderate differences. There's a lot of scatter here, but those large bedrock plains that I showed you a minute ago actually plot down in here. These were kind of just broken up by general region, not by shape or anything like that. In Terra Sabea, we saw higher olivine abundance, which is around 5% higher than the surroundings. And in Terra Samaria, we actually saw that these large bedrock plains have lower olivine abundance than the surroundings. They all tended to plot down in here. And finally, we saw that Terra Sabea bedrock plains are really predominantly heavily eroded surfaces, very few small craters. See a lot of layering involved with these, deeply textured surfaces. And we see some of these apparent preserved ancient channel systems associated with them. In Terra Samaria, we see these really resistant planar surfaces. And here's an example of some spectacular flow-like examples I found or flow-like textures that I found while I was mapping. This is presumably a vent of some sort, and you might have just lava just spilling out from all over it. It's really cool. I am still working on the Terra Samaria story. I'm not ready to talk about that in a whole lot of detail today, so I'm just going to focus in on what we did with the Terra Sabea bedrock plains. So I realized that I talked about olivine without really introducing it. Olivine is a material that forms in magmatic conditions. So if you see it on the surface, it was either erupted by lavas or was exhumed from really deep within the planet. And this mineral is really unstable when you expose it to water, even in a cold, dry Mars climate. If you're forming valley networks and have liquid water present at points in time, these minerals are probably only going to survive between 20 and 100 million years. And you can see what happens here. These nice green crystals here are olivine. Here's a fresh basalt that has olivine in it. And over time, interaction with water will basically just rot these crystals out. You can see they've basically turned to a mixture of rust and clay. So it's really interesting that we're seeing these potentially sedimentary plains have higher olivine abundance. Like, how do you generate a sedimentary material that's olivine rich and then preserve that through deposition and whatever alteration formed a rock? So a few observations that we made is one, that our spectral olivine enrichments appear to increase with the amount of surface erosion that we were seeing. This is basically just tying olivine enrichment to these qualitative texture classifications that I mentioned. And another thing is that these olivine spectral signals originated from appear to originate from regions with high sand coverage. So our thought here is that we actually don't have a lot of olivine in the bedrock. And what's happening is you have little bits of olivine here and there that are preserved in bedrock. And because olivine is a pretty dense mineral, if you're blowing stuff around on the Martian surface, you might be concentrating it during transport. So I'll just show a quick example of what we mean, or what I mean by this. These two stars show the locations of high-rise images that I'm about to show you. One has olivine signal, the other doesn't. And we can see that the surface with a strong olivine detection has a lot of sand on it. surface with a weak olivine detection doesn't have a lot of sand on it. So to really study this closely, we looked at Themis data. We took advantage of a small change in the mission. Basically, for most of its lifetime, Themis, the orbiter that Themis was on was in a sun-synchronous orbit that would pass over the surface between 2 and 4 p.m. local time. Later, or just a few years ago, before Opportunity passed away, may she rest in peace, the orbiter was moved to a later time to kind of help support these operations, or support that rover's operations. And a lot of the scientists on Themis were thinking this is basically the end of Themis spectral data collection. The surface is just going to be too cold to really get good high quality spectra. But it turned out that that's not really the case. If you look in the summer, the surface is still pretty much warm enough that you can get a decent spectrum from the surface. And so this provides us with an opportunity. If we can measure the spectra at different times of day, we can take advantage of the changing relative temperatures of sediment and rock to kind of untangle the compositions of these materials at scales below what we can actually see with a single Themis pixel. So just to show an example, radiance, or the amount of emitted light here, is on the y-axis. A temperature with a theoretical thermal inertia is plotted along the x-axis. And you can see in the daytime imaging, the sand components are brighter than the bedrock components. In this case, about 20% brighter than bedrock. And in the evening, that turns around. The sand is now darker than bedrock, and the bedrock is about 25% brighter. And this is just for a single observation pair. This is kind of variable, but this is kind of the idea that we're working with. So we have small amounts of olivine that are preserved in the sedimentary rock. Or to come back to our hypothesis, we have small amounts of olivine that are preserved in sedimentary rock, concentrated in the sand cover by erosional processes. And if this is the case, then we should see that the olivine abundance declines over the course of the day, because if it's in the sand is becoming fainter, the olivine signal is becoming fainter. So this really just kind of shows how different the surfaces look. If you remember earlier, I said that purple surfaces are silica poor, green surfaces are more silica rich. Comparing these DCS stretches just at different times of day, you can see that even just the color of the surface changes dramatically. And that's telling us that something spectrally is up. There are changes that are occurring. So once we find these overlapping observations, we run a thermal model just to make sure that we are seeing big enough changes that we can measure, or that are theoretically measurable. And then we model just mixtures of sand and bedrock at these temperatures and figure out how much, or the magnitude and direction of change, or figure out the magnitude of change and see if what we're actually seeing is consistent with that. So generally in these plots, we should, just to illustrate this, the emissivity minima for a silica-rich rock is over here. If you add olivine to it, or an olivine-rich sand to it, it should move the spectrum to the right. So we compare these emissivity minima, and we'll just quickly show, kind of spoil the results. We see that the evening image, or the evening spectrum, has an emissivity at longer wavelengths than the afternoon spectrum, which is the opposite of what we expected to see. So the conclusion is that we only saw one bedrock plane that had strong evidence for higher olivine abundance in sand, and luckily for me, the place where we saw that happen was the place where I developed the hypothesis. So good job me, I got it right in one place, but it turns out that's not really applicable to everywhere else. And so the Bedrock appears to be hosted in, or the olivine appears to be hosted in Bedrock. And probably the most likely way that you're getting this is you're erupting large amounts of pyroclastic material onto the surface. These would contain olivine, but they would not necessarily be hard rocks like lavas. These are probably just easily eroded, really friable pyroclastic deposits. And to bring that back to this kind of paradox of why do we see, why do the older rocks have less regolith on top of them? The answer might just be because they're more easily eroded. They're not lavas, they're just pyroclastic materials. And what we're seeing is a transition from more explosive pyroclastic activity to more effusive lava flow types of activity over Martian time. So this is where my career just jumped ship, and I end up on MSL team. I applied for and got an internship with Eileen Yinkst, who is now the PI on the Mars Hanlon's imager camera, camera on the Curiosity rover. And Curiosity was landed in Gale Crater. As the recently retired Ken Edgett liked to point out, Gale Crater is pretty much the deepest hole on Mars. Outside of the Hellas Basin, this large ancient impact crater that really blasted down almost to the mantle. Gale Crater is basically as deep as you can get on Mars, or as deep as you can find on Mars. This 150 kilometer wide crater is about 3.5 to 3.8 billion years ago. And what's really interesting about it is that it has this large interior mounds with a layered sedimentary deposit inside of it. So I'm just going to show a really nice oblique view that was rendered out by Sean Duran, who's on Twitter, who's very big in the space art scene. This is just kind of showing an oblique view across the mound, and this white line is the Curiosity rover's traverse. And so from orbit, we've mapped out some different units. We have this kind of crater floor unit that has a basaltic composition. We have these clay-bearing rock layers that Curiosity has since confirmed and found clay basically across this entire interval, and even down in here. And then above it, we have these sulfate-bearing layered rocks. And as of last week, I think we announced that we have indeed found sulfates in this unit. So far so good. And then above it, we have these spectrally bland rocks, and no one's really sure what these are. There's not really a strong spectral signature to them, and kind of the assumption is maybe that they're just large-scale dust deposits that have been cemented somehow. So I'm focusing on the Pahrump Hills outcrop. It's this little notch in the traverse path here. But first, let me back up and talk about Molly. Molly is an arm-mounted camera. It's pointed out with this arrow here. And it can be placed as close as 1 centimeter from the rock surface. And it can resolve features as small as 40 microns in size, which is about a 2 by 2 pixel thing. But what's really cool is that at maximum resolution, the image scale, one Molly pixel is about one wavelength of light that Themis can see. So just the difference in scale is just mind-bending. So here's the Pahrump Hills outcrop from a mosaic that the rover took just before it got there. It's really this first exposure of clay-bearing rock that we could identify from orbit that we could tell was contiguous with the main clay-bearing layered rocks. And Curiosity really Curiosity applied the technique of just reconnoitering the outcrop. Geologists do this all the time on Earth. We can just walk around the outcrop. We see something, we can just save it for later and then come back and compare and contrast and all sorts of different scale observations or different. We can just return to observations and supplement as needed. This really isn't how a rover works. It's you drive, you look, you drive, you look, and if you missed something, you missed it. And really the reason we don't do this is you can see, this is a map that Phil Stuke put together. This is Sol 751 when we got there. This is Sol 949 when we left. We basically spent a whole Earth year not traveling outside a 100-meter radius. So there's a reason we don't do this very often. The outcrop is kind of roughly divided into 3 target types: these recessive laminated mudstones, resistant laminated mudstones, and these cross-stratified sandstones. So these recessive laminated mudstones are generally down here. The resistant laminated mudstones are generally up here, and the sandstones form these these lenses inside the outcrop here. So just to kind of give you an overview of what these look like, this is a mass scan mosaic of these surfaces. You can see these really fine laminations, not a whole lot of relief. When we use the dust removal tool to kind of clear off some of the dust to look at these more closely, they were really easily gouged, which means they're really soft. There's nodules all over. You can just see them just sprinkled all across the rock here. And occasionally we see these scattered occurrences of intergrown tabular crystals, which are probably sulfate minerals that were growing within the sediments during or shortly after deposition. These resistant mudstones, you can see they're really highly textured. You can see some hints of lamination here and there, but there's something different about these. They're less soft, and they're more variable in appearance. This is probably more of a siltstone, but this is also kind of associated with those. It's the Chinle outcrop. And then you have the sandstone lenses. There's not really a great photo of this outcrop, but you can see these kind of coarse looking layered rocks. So if we look at moly up close, we can see that the matrix generally not resolved. We don't really see grains in these kind of intervals here. But these laminae, these individual laminae seem to be 1 grain thick, about 200 to 800 micron size grains. And what was probably, so you can see the laminations in a side view here, and we see these truncation surfaces that cut off some of these laminae. So our interpretation of just from this image is that the environment generally favors suspension settling. That's how you're depositing mud on a lake floor. If there's too much current, that mud just never settles out. And these laminae might just be more significant pulses of activity. You're basically flushing in a little wave of sediment and leaving it there. And some of these pulses were strong enough to actually start scouring into the surface, which forms these truncation surfaces. So here's some of these crystal forms that I've mentioned. I don't really have a whole lot of time to go into these, but these are probably pseudomorphs after gypsum. And the analysis by Linda Kay suggests that these were forming basically around the time of deposition. Let's see. Beneath these sandstone lenses, we're seeing these mudstones start to coarsen into siltstones. These siltstones are coarsely laminated. This is one of those siltstone targets. You can sort of see like a grittiness to it. The grains aren't fully resolved by moly, but you can tell that there's actually texture there. And above these, we start getting more and more coarse material. These are the sandstones. You can see all of these grains embedded in a dark matrix. And here's a really spectacular close-up. You can actually see like the crystal forms. You can see zoning inside of these crystals. These are really cool clasts. The bimodal grain size of these sandstones indicates that there was a rapid deposition of the sediment load. Katie Stack has talked about these being hyperpycnal plumes. Basically, you're flushing a sediment-rich material into the water, and it's all just dumping out all at once. And so this sequence here might record the approach and passage of a fluvial outlet. We also see these really cool concretions all across the outcrop. And these appear to be, sorry, I got a little lost. These appear to be forming along fractures, and you might just have water kind of puddling up and forming a geochemical membrane. It's kind of an interface between waters inside of these little veins and the surrounding and remaining pore waters. Whenever these membranes rupture, the fluid in here kind of spills out and forms another membrane, and you grow these by aggregation. And we just see different forms of these. There's also these types of concretion called stack concretions. We really only see those along laminae. They seem to be an unusual type of concretion, even in Pahrump hills. Some of these laminae some of these stack concretions kind of grade into the surrounding laminae, and so we just have these laminae that are more cemented, but not necessarily concretion forming. And some of these rock surfaces, appear to preserve texture differently. We can see these weird preserved grains, maybe small concretions. It's hard to tell due to the scale of these, but there's something weird going on with these rocks. And kind of the impression that we got from looking at these rocks are some sort of diagenetic sequence. We have these mudstones with these grain laminae. With a little bit of water, these kind of start getting these concretions along the laminae. With more water, the whole rock starts changing. You get this weird textured surface. And eventually you basically hardened this whole rock into something more resistant with the grains just embedded in it. So out of time here, so I'll just quickly say that the Pahrump Hills deposit likely records a lacustrine environment, nothing particularly new, but what Molly tells us is that this lake was probably saline, possibly shallow. The sediment deposition appears to have been pulsy and probably over a long period of time. We occasionally get these really significant pulses of water in there, some of which form little truncation surfaces, some of which are depositing sandstones. And then sometime after the rock was deposited, we're seeing this kind of differential hardening of the rock, of the sedimentary mass. So kind of a whirlwind tour. Need to stop and catch my breath here in a second, but I will just power through the summary. So if we want to look at rock from orbit, the ancient cratered highlands are really not a bad place to look. What we see from orbit appears to be pretty diverse. You see all sorts of activity going on, all sorts of weird preserved landforms. And specifically, one of the things that I found is that the evidence for extensive pyroclastic activity in the Martian environment may be a lot more extensive than we previously realized. looking at rocks from the ground, it's really helpful to take a really close look, and our analysis using MOLE imaging supports kind of this interpretation of a dynamic nearshore environment at Pahrump Hills. So moving forward, I need to wrap up the Terra Cimmeria volcanic plains chapter of my dissertation. I've got a chapter that's 2/3 done and probably publishable soon. But as I've moved on to rover work full-time now, I'm really looking at trying to apply these MOLE grain scale analyses to the clay sulfate transition in Gale Crater. This is where we see those clay-bearing rocks change to more sulfate-bearing rocks. And I want to work out whether that's a major compositional change that represents changing depositional conditions or some later geochemical overprint on the rocks. I'm also really excited to be able to share soon some work that I've done with the Mars Descent Imager. This is a camera mounted underneath Curiosity that took pictures as it was landing. And I'm working on collecting drive movies with these, and I'm using the images taken with those drive movies to compare rock textures at millimeter scales to rock textures that we see from orbit. So I'd really just like to quickly thank my dissertation advisors, Deanne Rogers, my postdoctoral advisor, Eileen Yinkst, and all of the wonderful support that I've gotten so far from the MSL project. So with that, I will stop and take any questions.